We're going to expand on the concept of exothermic and endothermic chemical reactions. And remember, this is all about the exchange of heat. So, when chemical reactions happen, what's happening is you're breaking the bonds of the reactants and then you're making bonds in products. So, in order to break bonds, you need to add energy. So, if you think about maybe some magnets that are stuck together, in order to separate them, you would have to use energy to separate them. But then when magnets go back together, you can kind of release them and they'll go together themselves. So it is endothermic, meaning we have to add energy to break bonds, and we get energy back when we're making bonds. So it's exothermic. New bonds made release energy. So chemical energy is stored in the chemical bonds of a substance. So anytime you eat anything, that's the kind of energy that you're looking to get. You're looking to get chemical energy. So chemical energy is extremely important to us. That's the kind of energy that we get from food when we eat food. Chemical energy is also the kind of energy that we use in order to get fuels for our house. Natural gas is a hydrocarbon, and we use that to cook our food on our stoves. We use that to heat our water in our hot water heaters. We use that to heat our homes. So chemical reactions always involved energy change. Making bonds and breaking bonds always involves energy changes. So you might remember talking yesterday about the bonds. For example, let's talk about the natural gas that's in here or the gasoline that's in your car. Those are hydrocarbons. Would it surprise you to know that they are considered inert or non-reactive? So what do you think would happen if I had a bucket that was filled with gasoline and I took a lit match and dropped it in that bucket? What do you think would happen? It would explode. Would it surprise you to know that the match is going to go out every single time? In order to prove a point, they actually did an experiment. And they dropped 1,000 lit matches into a bucket of gasoline, and each and every single time it went out. So let's see if we can wrap our brain around this concept, because you know there's a parking lot full of cars out there, right? And they're all filled with gasoline. There's natural gas in here, right here, waiting for us to turn it on and light it with our Bunsen burner. Does anybody really sit around and worry about these exploding? You drive past gas stations. Do you sit there and say, oh, I don't want to go in for get myself a Coca-Cola. I don't want to do that because this gas station might explode. We don't ever think that, do we? That's because they're really non-reactive. They're really inert. That's why they store so much energy. So the energy that we need to add to them to get them to react is called activation energy. So the energy required to break the bonds in the reactants for a chemical reaction to occur is called activation energy. Without adding that particular type of activation energy, the chemical reaction most of the time will never happen. So we must supply a certain amount of energy to get bonds to break. And in the case of the hydrocarbons that we get a lot of our fuel from, it's actually quite a bit of energy that we have to add. And that's why these types of reactions don't occur on their own. That doesn't mean that there's no explosions, but there has to be some sort of event to get that to happen. So endothermic and exothermic reactions both start the same way. Step 1, energy must be supplied to break the chemical bonds of the reactants. Step 2, energy is released when new chemical bonds are made in the products. So what happens is, remember, matter cannot be created nor destroyed. Energy cannot be created nor destroyed. So what happens in a chemical reaction is there's a rearrangement of the atoms involved. So the same amount of atoms are in the reactant side as the product side. We know that from balancing reactions. They just get rearranged. And this energy that is either absorbed or released, we don't create that energy. We change it from one form to another. So a reaction is exothermic if more energy is released from the products than we had to supply to the reactants. If more energy is supplied to the reactants to get the bonds to break than energy is released in the products, then the reaction is endothermic. So it's a comparison between the energy of the reactants and the energy of the products. So based on the type of energy involved, chemical reactions are classified as either exothermic or endothermic. Exothermic energy is released. Exo, in this case, means exit, such as the burning of gasoline or any of the fossil fuels that we burned. All combustion reactions are exothermic, meaning they release energy. Endothermic means energy is absorbed. Energy goes into these chemical reactions. We do that every day when we cook food. We have to add energy to get our food to cook. You know that if you go home and you crack an egg and you put it in a plate, it's never going to cook itself. We have to add the energy in order to get that food to cook. So here's what an endothermic chemical reaction diagram looks like. If you notice, you can compare the energy of the reactants and the energy of the products. The products have more energy than the reactants. So that tells you that it is an endothermic process. The difference or the change in energy for this reaction is the difference between the reactants and the products. That tall part in the center there, that's our activation energy. That's how much energy we need to add to get the reaction to happen. Up at the top there, we'll have what's called activated complex or a transition state. So that's how much energy it requires to break these particular bonds. In this particular reaction, because it's endothermic, energy was absorbed because we know that because the products have more energy than the reactants. So these are all the different pieces and parts of this reaction diagram that we can analyze and calculate the amount of energy involved in reactions. So what's going to happen is if I had a beaker in my hand and I was doing an endothermic reaction in it, the beaker would feel cold. And you're going to say to yourself, wait, if it feels cold, then how could it involve an increase in energy? Well, you always have to worry about what is the system and what is the surroundings. If you have a beaker in your hand, the system is actually inside the beaker. That's where the chemical reaction is taking place, is inside the beaker. And your hand is going to feel cold because the chemical reaction is going to pull energy from your hand. Just like when you touched the leg of your desk yesterday, it felt cold. That's because you were feeling the heat leave your hand and enter into the desk. Remember, there's really no such thing as cold. It is only the absence of heat. So when we see endothermic reactions, energy is written as one of the reactants because energy has to be added to the reactants in order to get the chemical reaction to happen. Usually that energy is in the form of heat. Not always, though. Light can do it. All sorts of things can start a chemical reaction happening. But a lot of times, especially for our purposes, it is heat. Now let's look at an exothermic reaction diagram. An exothermic reaction diagram, check this out. See how the activation energy is a little bit smaller for this one? And the energy of the reactants is actually greater than the energy of the products. That means that in this particular case, energy is released from this reaction. So what's going to happen is you're going to add energy to the reactants in order to get the chemical reaction to happen, in order to break the bonds of the reactants, and then energy is going to be released when we make new bonds in the products. In this case, Making new bonds in the products releases more energy than we had to add to the reactants. There is a net release of energy in an exothermic reaction. So if I had a beaker in my hand and I was doing a chemical reaction and the beaker felt hot, that would be an exothermic reaction because the system is actually inside the beaker. So it feels hot because the chemical reaction is releasing energy to our hands. So in this case, energy is written as a product, either as energy or heat. Usually we release heat when these are exothermic reactions. So can you look at these and classify them as endothermic or exothermic? What we can do is check out what's going on here. Energy is written as a reactant in the first reaction, so it is endothermic. Energy is written as a product in the second reaction, therefore it is exothermic. So next we're going to take a look at a couple processes that we're used to. These aren't always chemical reactions. Chemical reactions are not the only thing that can be endothermic or exothermic. Physical processes can also be endothermic or exothermic. So let's think of a couple examples that we're all familiar with. How we decide whether it's endothermic or exothermic is we first have to figure out what the system is. And then we analyze the starting materials and the ending materials to determine which have more energy. And then we can classify them as endothermic if it absorbed energy or exothermic if it released energy. How about ice cream melts? You think that's endothermic or exothermic? Let's think, because we have cold ice cream, right? And then in order to get it to melt, we know that we have to add energy so that the melted ice cream will actually have more energy than the frozen ice cream. So that says endothermic. A salt is dissolved and the beaker holding the solution feels cold in your hand. Is that endothermic or exothermic? It's endothermic. The cold that you feel, remember there's no such thing as cold. You're feeling the heat leaving your hand. Iodine sublimes. Does anybody remember what sublimes means? When something sublimes, it's changed straight from a solid to a gas. You think that's endothermic or exothermic? So we start off with a solid, and we sublime it, we end up with a gas. So when it comes to solids and gases, gases always have more energy because their particles are farther apart and they're moving faster. So this would be an endothermic process. Campfire burns. What do you think, endothermic or exothermic? Exothermic. It is exothermic. The system is actually the wood. The system is actually a hydrocarbon because wood is a hydrocarbon. And when you burn it, you feel the heat coming off of it because it's an exothermic process. Steam condenses. It is a gas to liquid. So remember, gases have more energy. And if we take it down to a liquid, well, let's see. We start with a gas and then we change it to a liquid. So remember, gases, liquids, solids. So if we go from a gas to a liquid, does that give off heat or absorb? So we always have to really kind of think of the starting materials and the ending materials, which has more energy. How about your food getting cold when you're eating dinner? It is exothermic. And you might have, if you're helping your mom clean up after dinner, she might tell you, wait till your food cools down before you put it in the refrigerator. You don't want to put something in the refrigerator hot because what will happen is they'll give all that heat off to the other food that's in your refrigerator and can actually lead to that food spoiling. Here's one that's probably pretty easy, right? Fireworks explode. What do you think? It is exothermic. We know that if we let fireworks explode in our hand, it would hurt a lot because it would burn. You also know that when fireworks explode, you see light. Light is another type of energy. You're taking chemical energy and you're changing it to light energy and heat energy. What we're really looking for is the light energy, but a lot of heat is given off also. And we talked a little bit about that yesterday. Whenever you change one type of energy to another, heat is also released with that energy change. All right, water freezes. Here's another chance for us. Is that endothermic or exothermic? Water freezes. So let's see. You have water, it's a liquid, and it changes to a solid, which has less energy, right? So it's actually exothermic. That can be surprising, can't it? But they got all those citrus fruits. So they figured this out a long time ago. What they do is they spray the fruit with water. Then, as the water's freezing, it gives off energy to the fruit. So it gives off heat to the fruit. So that keeps the fruit itself from freezing. And then ice also acts as an insulator. So it also protects the fruit after it's frozen. So that layer of ice on the outside acts as a protective layer to keep the fruit from getting ruined. So ice is actually an insulator. You may have heard of people making igloos to stay warm, right? And it's actually a way to keep the fruit from being ruined, is by taking advantage of the exothermic nature of water freezing. This happens a lot too. This is a science term. Acid gets hot when it's diluted. So if I had a cup of acid in my hand and I added water to it, it would get hot. And that is an exothermic process. And our metal feeling cold in our hand, that is exothermic if you consider your hand being the system. If you consider the metal being the system, this can be thought of as two different ways. If you feel the metal being the system, then it is endothermic because the metal is absorbing heat from your hand. Okay, that's our intro to endothermic and exothermic reactions.